Hi, my name is Zhou. I am a software scientist in the Research Software Engineering Group in Oak Ridge National Laboratory. Thanks for having us to talk about PyRS today. PyRS is a data reduction and visualization software which is designed for an engineering neutron diffractometer which is called HiDRA, and it is operated in Oak Ridge National Lab. PyRS is one of the software that our group is developing, and I am one of the developers of this software. In this presentation, first I will give a brief introduction to one of Oak Ridge National Lab's neutron user facility, HiDRA, and the neutron diffractometer, HiDRA. Then I will talk about the neutron scattering experiment workflow and focus on data reduction. This will lead to the software requirement for PyRS. In the main part, I will present in details about the software development and also some techniques that we use. Beamline HV2B, with acronym HiDRA, is built to study residual stress, strain, and texture of materials like iron, steel, and various types of superalloys. These manufactured materials are widely used in construction industry. Residual stress of this type of material is of great interest to study. It can be detrimental to cause premature failure or early crack propagation. On the other side, with properly engineered, it could extend useful life, prevent premature failure, or increase safe elastic limit. Neutron diffraction is a unique technology to study these properties. It is non-destructive because neutrons are either traveling through the metal or scattered by nuclei. Because neutrons can penetrate metal, they can measure the inside of the sample but not limited to the surface. For example, a real jet engine blade was once measured at this beamline. With well-controlled motors, it is able to do spatial resolved mapping on large sample volumes. High Flux Isotope Reactor is the only research reactor operated by Department of Energy to study material science by neutron scattering. HiDRA is one of the 12 neutron instruments in this user facility. In general, for a neutron scattering instrument, neutrons are generated in the reactor and then travel through neutron guide to hit the sample, which is the material of interest. Part of the scattered neutrons are detected by neutron detectors. The science can be retrieved from how these neutrons are scattered. HiDRA is built for engineering diffraction. It has a especially large platform to mount sample. The samples, which can be a chunk of steel, even a jet blade or a motor engine, can be placed there to measure. On the other hand, a large space allows for complex sample environment device too. For example, a furnace for high temperature or a load frame for continuous loading. It has a two-dimensional detector, which is configurable to 2048 by 2048 pixels on a moving detector arm, while usually it is configured to 1024 by 1024 pixels to match the instrument resolution. For material scientists, who are the major part of the users for this beamline, their ultimate interest is to have a scientific data that they can directly use to analyze the material. For example, this is a 3D stress mapping on a large weld. A series of sample points were measured along the weld toe. The changing of the stress is what they are looking for. Thus, data reduction is an essential step in the whole workflow. It bridges the experiment and the science. In a simplified HiDRA data reduction workflow, the raw neutron events loaded from the raw data file will be converted to intensities histogram by the neutron diffraction angles. Bragg peaks positions, which are related to the crystal atomic structure, are obtained by fitting. Then the strain and the stress are calculated from the Bragg peaks positions, or the textures are calculated from these peaks intensities from various crystal orientations. The software requirements for PyRS are thus abstracted from such data reduction workflow. In HiDRA, event nexus file is the standard raw data file for most of neutron beamlines, including HiDRA. PyRS loads the neutron events from event nexus file. One experiment run will be recorded to a single nexus file. In most of experiments on HiDRA, one run may take a few hours to 12 hours or full day. Usually in such long run, either the sample environment or the sample will change, or multiple spots in the sample will be measured. The latter one is typical to measure 3D stress mapping on a large sample. For example, hundreds of grids in a chunk of steel are measured. Therefore, the loaded neutron events should be split and regrouped by user-specified criteria. The next step is to histogram these neutron events again by their diffraction angle to theta. The diffraction angle is directly related to the change of neutron's momentum, such that the diffraction pattern can be obtained. In the diffraction pattern, we look for Bragg peaks. Their position are a direct measure of the interplanar spacing in the sample. Because the instrument resolution is finite, the peaks are not delta functions but Gaussians or pseudovoids. Thus, accurate peak fitting is required. Finally, strain and stress can be calculated from the shift of peak positions. The pole figure is calculated from peak intensities of various crystal orientation. These calculations involve metadata from the experiment by sample positions or sample orientation, respectively. HiDRA is upgraded from an older instrument called an NSRF2. It had 7 smaller detectors comparing to the millions of pixels in HiDRA. Therefore, PyRS should be new generation software incorporating new features of the instrument and addressing new science and new challenges. Comparing to the last generation LabVIEW-based data acquisition and data reduction software, combined with Excel sheet and MATLAB scripts, PyRS should support at least 90% use cases and open to continuous development upon the emerging of new science. We develop PyRS in Python with scientific Python libraries and a graphical user interface. We choose PyQt in our case. HF5Py and Pandas are the replacement of Excel spreadsheet. Furthermore, the new Epic data acquisition system provides users with more flexibilities in experimental setup, and thus the data reduction software should support this new reduction workflow too. Usually in the scientific community, non-functional requirements are equally important. The software must be user-friendly. HiDRA is the unique engineering diffractometer in the world. A user may only use this instrument once in their lifetime, and means they use PyRS to process data once in their life. It is not expected for them to invest a lot of time to learn how to use PyRS. Thus, PyRS must guide the user with the right workflow with very intuitive design. It is expected that the HiDRA user will leave ONL with reduced data. They will run PyRS on SNS analysis cluster, so we need to consider the computation speed. It should be reasonably fast on the workstation. User can then process the data interactively. Memory is another issue. Each user's quota on our analysis cluster is about 50 GB. The data file from long measurement, say overnight or a day, could consist a large amount of neutron events. Without being cautious, The memory could be a bottleneck. A successful software project requires a good strategy of project management. A team is formed in RSE group to develop PyRS. In this project, we use agile programming and multiple development cycles. At the beginning of each development cycle, our team and the project owner, in our case the instrument team, will discuss the priorities of the tasks. GitHub project is used to organize the work to be done for the release. The workflow is automated as much as possible. In the peak of the development, there is a daily stand-up meeting between us and the project owner. Product owner uses the codes in the Git master to test and provide feedback promptly. In PyRS, we use the test-driven development combined with CI/CD. We can say that it is awesome to have GitHub working with Traverse CI. We use Flaky and the code curve to examine the programs for the formality and the code coverage to make sure the codes are healthy. And we use PyTest for unit and integration test, and the PyTest Qt for GUI widgets. The PyRS master is deployed to analysis cluster by using rsync. PyRS is composed of backend and front end. The front end provides the GUI for manual reduction, peak fitting, texture analysis, and string stress calculation and visualization. The auto reduction and instrument calibration are Python scripts. The backend contains the data structures abstracted from physics quantities. They include neutron events, diffraction patterns, the peaks with all the parameters, sample logs, and other data objects. Reduction algorithms are built upon these data structures for the reduction workflow. They include nexus conversion, diffraction pattern generation, peak fitting, string stress calculation, pole figure calculation, and instrument calibration. The process to load the neutron events, split them according to user-specified criteria, and histogram them to pixels is the first step to data reduction. Meanwhile, this step requires good algorithm for performance both in time and space. In the neutron facility in ORL, the neutrons detected are recorded as neutron events. Each event contains the time, say when the neutron is detected, with a precision to 100 nanoseconds, and the location where the neutron is detected. Thus, in the Nexus file, the neutron events are recorded as a list of pulse times. Each pulse is about 0.5 seconds apart, and it might drift in long run, and the number of events in each pulse. Then, in the order of time that the neutron events are detected, a list of relative time of each neutron events are presented. And there is another array with the same size of neutron events is the pixel ID for the neutron being detected. So we can use this one to calculate where the position. This is an example if we look at the Nexus file, which is in HDF5 format. Combining the event ID and the offset of the time, it is a description to a neutron event. For example, the 14th event, the time of flight, which means the time flying from neutron source to detector, is about 6,000 times 10 to the minus 6 second, and is detected on pixel 509337. The time 0 is the starting time of each pulse, and the event index is the number of events in the pulse. From the example, we can see that there is no event in pulse 0, and the first 718 events are in pulse 1. Meanwhile, the split criteria is usually obtained from the sample environment data, or what we call metadata. In Nexus file, the metadata are recorded as arrays. One array is for the relative time to the run start when the metadata is changed, and the second array is the value that the metadata is changed to. By understanding this data structure with help of H5Py, all those 4 arrays are loaded to numpy arrays. In order to regroup all the neutron events time with some specified sample environment parameters, the first step is to generate a list of time boundaries for event to split with. Then we use the numpy algorithm, search sorted, and bin counts. The neutron event can be efficiently split and regrouped. Even an overnight data file won't take more than a few seconds, or maybe even under a second. Memory is not an issue, as the maximum memory required are number of events that numpy arrays handle it very well on our analysis cluster. The next step is to calculate the diffraction pattern from the neutron counts on each detector pixel. The main algorithm is straightforward. By the position of each pixel combined with the sample and the reactor source, the true theta diffraction angle can be calculated. Then all the pixels are histogrammed on its diffraction angles with the neutron counts as its weight. The relatively complex algorithm is how to calculate the pixel positions. The detector is moving about the sample, thus the pixel positions will be calculated at the real time when the detector arm angle is read in from the metadata. Also, since the detector's mount on the arm is not exactly the same as the engineering positions, and even these shifts are small, but still could affect the peak resolution, so they should be considered. The algorithm to calculate the detector pixels' positions involves a series of shifts in vector and vector matrix multiplications for detector rotation. As numpy arrays have the main data structure, these operations on an array with 10 to the power of 20 elements can be finished in seconds. In our early development, back to 5 or 6 years ago, we used PyQt 4. Then we started to use PyQt 5. One major issue that we encountered was that for all the workstations in our analysis cluster, they are heterogeneous to support PyQt 4 or 5. Thus we end up like this to import the right version of PyQt. Of course, this is a pretty bad solution. The elegant solution is to use QtPy, which is an abstract layer for PyQt 4 and 5, and PySide 2. It automatically figures out which version of PyQt of the OS that the software will be running on. As we know, Qt6 is coming in November 2020. We expect to use QtPy for Qt 4, 5, and 6 compatibility. Another issue is that the Python files compiled from the Qt UI file, it is very sensitive to PyQt 4 and PyQt 5. So we use PyUIC4 and PyUIC5 initially, and it had issues when we deploy on the NS cluster. Then we used the load UI in QtPy to translate UI to Python dynamically, and it's very convenient. In PyRS, we have two reduction interfaces. One is the GUI for manual reduction, such that the user can interactively process and visualize the raw data and the diffraction pattern. It is very helpful for user to examine subruns in a continuous measurement. The other one is auto-reduction script, which is run by our auto-reduction service. The reduction status is posted such that users can know whether they have the data ready for further process. Peak fitting requires more involvement from the user, though we have developed decent algorithm to estimate the starting value of peak parameters automatically. We will still provide users with an interactive interface to select one or multiple peak regions for fitting. The result of the peak fitting can be visualized in various ways. A table contains all the fitting results of all the peaks. A 2D plot allows users to plot any two quantities, including peak parameters and metadata. When we plot these parameters against each other, we can check their correlation. Three-dimensional view of fitted data with metadata as one more dimension for the scientist to explore such kind of correlation. PyRS has been deployed and used on a daily basis when the Reactor in HiDRA is running. If you are interested, you may check PyRS on GitHub. Their PyRS project, we have proved that following rigorous software engineering procedure is a good practice to develop a robust software efficiently in the DOE user facility. Scientific Python libraries plays an essential role to support the neutron scattering science, from data reduction to analysis and visualization. Now more and more scientists can write Python script to prove their idea, and it is convenient for us to transform these prototypes to software. The PyRS project is sponsored by DOE, and it is an open source software. It uses algorithm and data structure in multiple scientific Python libraries, and also from the Mantid project. Thanks very much.